scalar multiplication in the polar identity. So what we have shown, we have shown that for all x, y, z belong to H, inner product of z plus x comma y, this is equal to inner product of z with y. Inner product with x with y. So what we want to do, so if the second part linearity, that is the scalar multiplication. So if alpha belongs to f, where f is the field. Okay. Now the point is that in our case, f is either R or C. What is this part? So if you look at this part from here, if z is equal to x is taken, what do we get? Inner product of x plus x with y is what? Inner product of x with y, x with y. Z is equal to this is nothing but so what we have got is that 2x comma y is the same thing as sum of these two terms over here is 2 times inner product of x with y. So similarly, inner product of 3x comma y is the same thing as 3 times inner product of x with y. So if n belongs to the set of natural numbers, we get that inner product of nx comma y is what? N times inner product of x with y. So we extend it to the negative part also. So how we do that? Since for all we had that inner product of zx plus x with y, this inner product is z with y plus inner product of x with y. Let z is equal to minus x. So what do we get? 0 with y. So this is by the definition. We are getting that this is inner product of minus x comma y, product of x comma y. What is this by definition? This is not the inner product. We are writing as a symbol, but yet we are proving it's in fact an inner product. So this is inner product by the norm. that is below. If you look at this object over here, this is nothing but this term would be norm of y square minus this term is norm of y square plus I times, since norm of y, you will see that that is 1, or rather norm of IY whole square, and minus 1 norm is there. So here with I is there, no term, I times minus I times this term norm of IY whole square. This term cancels out with this term cancels out this term. So this value is 0. So which is this value. So what do we get? This is equal to 0. So what does this imply? This implies that minus inner product with x with y. This plus this is 0. This is minus inner product of x with y. In other words, then this clearly implies that inner product of the same argument 2x comma y would be minus 2 times inner product with x with y. Continuing this thing, so this n which was there, now this can be replaced with z. So for all n belonging to z, inner product of nx with y, this is n times inner product of x with y. Now extending this to rationals. How do we extend it to rationals? Let's say consider the following number, maybe say 1 by n x comma, okay, so 1 by n x, since B is Banach and F is a field either R or C, 1 by n belongs to F. So 1 by n multiplied by x belongs to B. If x belongs to B, that's the case. So let's call this object as x dash. This is nothing but inner product of x dash with y. And clearly n times x dash is equal to x. Because n into 1 by n x is x. And how is that case? This is 1 by nx plus 1 by nx. Continue. This is n upon n times x, which is x. And we know that n times x dash comma y, this is n times inner product of x dash with y. But n times x dash is what? This is nothing but inner product of x with y. This one, writing just the definition of nx dash. This is this terms. The shifting n on the left hand side. So what we have got? We have got that 1 by n x comma y is n times inner product of x with y. That clearly implies that inner product of So once this is done, similarly this is true for all n belonging to natural number, and similarly all n belonging to set of integers minus 0. And since if you want p by qx comma y, where p and q belong to z, q not equal to 0, this would be nothing but p times inner product of x by q with y. Then this x by q plus x by q added p times, and then by this part p is integer, p by q inner product of x with y. So for rational scalars, linearity is done. Now we'll use a fact. Rationals are dense in Q. So if R is any real number, there exists sequence such that alpha n converges to R. So the property of the norm is what? The norm is a continuous function. That would clearly imply that alpha n x plus y would converge to norm of alpha rx plus y. Norm of alpha n x minus y would converge to rx minus y. Norm of I times, if you want, if you, more generally, minus would converge to minus of this value, I times I alpha n x plus y. If f is equal to c, that would converge to I times rx plus y minus I times minus I alpha n x minus y would converge to minus I rx minus y. So I here, I is there, I is there. Or rather, what I would say is that let's take iy plus iy, and here this would be just rx plus iy minus iy. And adding all of this thing is clearly nothing but squaring and so on. Square is this thing, square is this thing. This square, this square, this square, this square. And then you add all of these things. This clearly implies that inner product of would converge to what? But this is nothing but because alpha n rational, and we have already shown for rational, so this is 4 alpha n times inner product of x with y. This value is this value, but alpha n converges to what? R. So this converges to 4r times x comma y, but this is this value. So what we have shown is that rx comma y is indeed r times x comma y, where r is what? Real number, x and y belonging to be in. The same proof works for complex scalar. So how do I get complex scalar? Q plus IQ is dense in C, since C is made up of R plus IR and Q bar is equal to R. So Q plus IQ whole bar is R plus IR. This is done. So just the first property, so linearity we have checked. Non-negativity is easy to see. Why is it the case? The norm. So inner product, so linearity and triangle inequality, or rather the triangle inequality is arising from the norm, but the linearity is checked, alpha and so on. So complex conjugate, just a property. So inner product of x with y is nothing but this is 4 times, this is defined as here just y is there. Alright now. And y with x is what? I times this part is as it is, this part is as it is, this thing, minus mod of norm of 1 is equal to 1. From here, if you take I outside, minus I rather, if you take minus I, so this becomes minus I and so on. Observe that minus I times minus x minus IY is y plus ix, and norm of minus I is 1 and norm of minus 1 is also 1. So, but I is a scale, so unit norm and so on. So what do we get is that this is just x plus IY here, right? Just let's write more properly. So I have what term over here? X plus IY, y plus ix. If I take I common, what do I get? So rather taking minus I here from here, what's IY? And norm of I is what? 1. I have, so this term gets replaced with x minus IY. If I take I common here, I get I or minus I common, so x minus, I should have plus, because I square is minus 1 minus minus 1 is y has plus sign. So this term, but you have x plus IY with a minus sign here, and x minus IY with a plus sign. So it's clearly, if you look at above over here, is x plus IY is with plus I sign, x minus IY with minus I sign. So from this observation, it is clear that this value is the same thing as since 4 is a real number, x comma y bar is for all x and y belonging to B. We're done. The complex conjugate part. And x with x is easy to check that. Inner product of x with x would be nothing but 4 times x plus x whole square minus norm of x minus x whole square plus I times norm of x plus ix whole square, x minus ix whole square. This is clearly 0. Norm of a0 square is 0. Norm of 2x whole square, x plus ix, what comes outside? X comes outside, 1 plus I times, and norm of 1 plus I is nothing. Square is what this, it would be square root of 1 square plus 1 square, its square, which is root 2 square, which is 2. This is I times 2x. So I times norm 2x rather. Minus I times 2 norm x square. Similarly, norm of 1 minus I is also 2. So this cancels with this thing. What is remaining is this term. But this is clearly 4 times norm of x square, because 2 comes outside and 2 square is 4. 4 cancels out. This proves what? Inner product of x with x is norm of x square for all x belonging to B. So what we have shown? We have shown that if the complex Banach space with parallelogram law and if you have this kind of relation, so then this Banach space is indeed, so this defines inner product and in fact is Hilbert space. Similarly, what can easily be shown is that for a real Banach space, with parallelogram law, and the inner product would be 4 inner product of x with y. Square.